Now we'll see pipelining model. In pipelining model, first thing you learn that we divided our hardware circuit into 5 stages, right? So each stage we prepared such a way that example, there is some work right in the stage. So the work whatever we are doing in that stage is maximum 200 picosecond time, correct? So what we do is we fix our clock cycle to exactly 200 picosecond, and that clock cycle time is exactly equal to one stage time. But in serial execution, in non-pipelining model, we fixed our clock cycle to exactly equal to one instruction execution time, which is nothing but 800 picosecond, right? But here what we are doing is we will be taking one clock cycle as one stage time, okay? And the stage duration is already fixed, right? So what is it? It is 200, right? It is maximum stage delay. So now what is going to happen is, just forget about this entire picture, just focus on the first row. What is going to happen is, so the first instruction will be, now you have a hardware, right? If you see the hardware, that hardware has 5 functionalities, right? 5 components. Otherwise, whatever the number of components, they can be designed such a way that they do instruction fetch, and they can do decoding, and they can do execution, and they do memory access, they do write back. Please go through that control unit topic where I explained the hardware, right? So we have seen the entire hardware unit. So all are independent. We such a way we planned them so that, so when you are fetching the instruction, then really decoding and that execution hardware and that memory write back, memory write, otherwise memory access stage, and the hardware related to write back, otherwise they don't have any work, right? In that way independently we designed. What I want to tell you is, when you are doing instruction fetch, then this decoding circuit and execution unit like arithmetic and memory access, what is the meaning of doing memory access? There will be main memory and we will be accessing the memory. How it is related to decoding, right? So that's why, so there is no relation between memory and these stages, they are independent. So there is no dependency in the circuitry, right? But only one question you might ask, sir, instruction fetch, in the instruction fetch we are going to fetch the instruction from memory, right? Which memory? Let us say main memory. And in memory access, what are you doing? We are also fetching the operands here, right? Where from where? Main memory. Sir, there is a clash, right? You have two stages. Really, if you want to do pipelining, then this stage and this stage should work parallelly, correct? At a time, simultaneously. But how simultaneously they work, sir? Because both requires main memory, and maybe example, let's say this is the memory bus, okay, through which we send the address, and there will be data bus through which we get the data. Okay, this is your main memory. Now instruction fetch stage and memory access stage require same main memory. How these two circuits can work simultaneously? They can't work, right? That's why remember one thing, the architectures, other architects are designed the machine such a way that there is a separate memory for instructions. Let us call it as instruction memory. Okay, so let us assume that we have two memory systems. One is instruction memory. How it is implemented doesn't matter. What is important for is we have instruction memory and data memory separately. Then only these two stages can work independently. Otherwise, there will be dependency between these two stages. Then it will be problem, right? Why it will be problem? If you want to understand, you should understand this entire flow of execution. How we are going to do the execution in pipelining. So far, we did not discuss how pipelining works in our, this model, right? In instruction execution we have seen in roti model, like how to prepare a roti with pipelining we have seen, but same thing of course here also, but we have not seen here explicitly. Let us do that. So at this moment you remember instruction and instruction fetch stage and memory access both requires memory. That's why what we do is we store instructions in separate memory and we store data in separate memory so that they can work independently. Remember it. Now with that situation you focus. So what I want to say finally is the instruction fetch hardware, decoding hardware, and this execution hardware and memory access hardware and write back hardware all are separate. So instruction fetch does not require any hardware about write back. Okay, so there is no dependency, all are independent. That means at a time you can make all these things work. If that is the case, what is going to happen is, assume that let's say I am using one clock cycle, let's say time period. One clock cycle is now 200 picosecond. In the previous example we took like this, right? So in the first clock cycle, what we are going to do is we are fetching the first instruction, okay, instruction number 1. Then in the second clock cycle, that means in the second 200 picoseconds, then we will be decoding that instruction. That's it. In the third picosecond, we execute that instruction. In the fourth picosecond, we do memory access if and all if it is there. Then in the fifth clock cycle, we will be writing back the result. Okay. Now, what I want to tell you is, in the second clock cycle, that instruction fetch stage or circuit related to that is idle, right? When you are decoding the second instruction, so instruction still the fetching instruction, that components are idle. Why don't you plan your machine such a way that, so in the second clock cycle, your machine's instruction fetch stage should fetch the second instruction. That is what you have to plan. For that we have to design hardware such a way. Okay. So that means, example, you have instruction fetch hardware, whatever it is. Okay, there is a hardware. We know how that hardware is going to fetch the instruction. Then we have to ask that hardware to fetch instruction for every clock cycle. Yes, because it requires only 200 picoseconds. In the second 200 picosecond, it can do it, right? If you ask such a way, we can design, not a problem. Why to wait for entire duration, right? So that's why. So the second instruction is getting fetched here. At that time, so the first instruction is getting decoded, right? So decoder circuit and fetch, that's why instruction fetch circuit and decoder circuit should be independent. There should not be any dependency. Now in the third clock cycle, we will be executing the first instruction, we will be decoding the second instruction, we will be fetching the third instruction. In the fourth clock cycle, we will be accessing the memory for the instruction 1, we will be executing the second instruction, we will be doing decoding of third instruction, we will be fetching the instruction of fourth one. In that way, so we can do. Now I can continue like this. In the fifth clock cycle, write back of first instruction, memory access of second instruction, and execution of third instruction, and decode of fourth instruction, and fetching the fifth instruction are possible simultaneously. Now after that, you see, in every clock cycle, 6th, 7th, 8th, 9th, if you have infinite instructions, then everywhere you can see that all the stages of your, see, this is the clock cycle. In this clock cycle, write back stage, memory stage, execute stage, decode stage, instruction fetch stage, all are occupied. So you get parallelism, right? Now we will see the time required to execute the first instruction, 200 picosecond. Already I told you. So pipelining doesn't add any effect in executing one instruction, right? But when you execute multiple instructions, you are going to get the better throughput, right? But for particular instruction, again it takes 200 picoseconds. Now in the second, sorry, not 200, it will be 200, 200, 200, 200, 205, right? So after 1000 picoseconds, we are going to get the first instruction execution. But then you see, the second instruction is immediately executed after 200 picosecond. Now after 1200 picoseconds, second instruction got executed. After 1400 picosecond, third instruction got executed. Assume that, let's say you are executing 10 instructions. How much time it will take? We will see for 10 instructions. Just let's list out. I1, instruction 1 requires 1000. Instruction 2 requires 1000 plus, see here. After 1000, just after 200 picoseconds, second instruction also done. So 1200. I3, 1400. I4, 1600. Now we can have a formula here. What is that? I4, 1600. I5, 1800. Can I say like this? 1000 plus, first time 0. Second one is 1000 plus 200. Third one is 1000 plus 2 into 200. I understood. So finally, I5 is 1000 plus 2 into the 200 into how many? You just check it out. I should get 1800. Can I say that 9? So 1000 plus, so here 200 into how many? 4, right? So 1800 I5. So what is this for? For this 5 minus 1. Then I10 equal to 1000 plus 200 into this 10 minus 1 9. So it will be 2800 picoseconds. Now let us use that old model where we have designed a circuit so that that circuit is intermixed in such a way that so one instruction execution takes exactly that 800 picosecond, right? Here the first instruction is taking 1000 picosecond here, but here 800 picosecond. It looks like it is better, right? But to execute two instructions it requires 800 into 2 1600 picosecond. To execute 10 instructions it will be 8000 picosecond. 8000 picosecond versus 2800 picosecond. Definitely it is better, right? Which one is better? This one, pipelined execution. Now we'll see the speed up formula. What should be the formula for speed up? If you want to know the speed up is nothing but, if you want to know the speed up for this problem or pipelining, because of pipelining how much performance improvement you got, that is nothing but speed up factor. Speed up factor equal to time required to execute. Example, let's assume that what is the speed up you get for 100 instructions, that is the question. You are executing 100 instructions. For that, how much speed up you are going to get? First of all, the formula, speed up formula is the time required in non-pipelining by time required to execute in the pipelined model. So that is the formula for speed up. Okay. Now let me repeat. If you want to know the speed up of pipelining for some 100 instructions, then the formula is time required to execute that 100 instructions in non-pipelining mode by time required to execute them in pipeline mode. Let us solve. So time required to execute them in non-pipeline mode is nothing but, so example, so all the details are previous details, like so that non-pipelined is taking 800 picosecond for one instruction. Then 800 into how many instructions? 100 divided by time required for pipelined. So time required for pipeline for 100 instructions, we have a formula. What is that? In this one, I10 is nothing but 1000 plus 200 into 9. Then for 100 instructions, that means you should know when the 100th instruction is executed, because by that time everyone is executed. So what is the time required to execute 100th instruction? It will be 1000 plus this 200 into 100 minus 1, 99, correct? So I can say that 1000 plus 200 into 99. 1000 plus 200 into 99. Right? Let us simplify it. It would be, can I say 800 into 100 is 8 into 10 to the power of 4 by 1000 plus, what I do is I write like this, 1000 plus 99 2s are 198, 19800. It would become 80000 by 1980 and 1000. That means, so 19,800 plus 1000. Is it not 20,800? Yes. So if I simplify it, 0 0 will get cancelled, 0 0 will be cancelled. So it will be 800 by 208. If I approximate it, like if I take in the place of 80, it will be 200 by 800, which is nothing but 4, right? Otherwise you get something 3.9 or something you get, you have to calculate and check. Finally, the performance improvement, if you see, through speed up, the speed up is 4 times, fourfold. So why fourfold? Why not fivefold? You have 5 stages, right? But see, the problem was in the linear, I mean that sequential model, the time circuit took is 800, right? But here these 5 stages are taking, because we took maximum delay, right? For each stage, though some stages are taking less time. In this model, what we did, because of pipelining, we took even delay, right? So in the pipelining, you remember, for better performance, all the stages should have same delay. Okay, that's why we fixed it to maximum delay. So 200 into 5000. So there we are getting the difference. So here you are taking 1000 picoseconds for one instruction execution, but in sequential execution you are taking only 800. But of course, because of the parallelism, we got the better idea. So at least 4 times is definitely better than nothing, right? So that's why pipelining is going to give the performance improvement because of the parallel execution, right? Now remember one thing, almost it is like number of, so that the improvement is one fold or two fold or three fold. It's like, if you have 10 stages, probably you might get a 10 fold performance improvement, but it is not always true. So why don't you divide our stages into 10 or 20? Because if you have 5 stages, then you are getting almost 4, right? That means 4 times. If I have 100 stages, I might get 99 times improvement in the performance. Is it true? No, it is not true. Why? We will see. Okay, I will tell you the reason.